now we're actually going to look at some real code.
Yep.
And tell us about what we're doing here.
Okay, so what we have here is a little toy program, and in this program, what we're essentially doing is we take this array of integers, 50 elements, let's just say, and what we're going to go ahead and do is go ahead and just fill this array up so that the first element of the array has the value 1, or has the value 0, the next element has value 1, the next element has value 2. So you could imagine if you were to get the value of P1 n, the value inside of it is going to be equal to n. Okay. So anyways, what we're going to go ahead and do next is now go and say, let's go ahead and go into the middle of P1, element 25. And we'll take that address and put it into P2.
Okay.
And then from there, we're going to now reassign P2 so that P2 is equal to the value of x plus y. So here's the value of x, which is minus 30. The value of y is 20. And if you do x plus y, that's equal to minus 30 plus 20, which is equal to minus 10. And then we'll go ahead and do the arithmetic with that and add it to P2. And then what we want to do is print the value of P2 at that point.
Okay.
And the question is, what should this program print? What is the, you go ahead, you compile this, what is the answer that you expect? And so let me go ahead and ask you, Charles, what's the answer here?
What's the answer that I would expect?
Right.
It's going to be 15.
Yeah, so that actually turns out to be an answer that a lot of people give.
But let's think about this now for a second. All right, no, but yes.
Yeah, so
that's wrong.
It's wrong and it's right. So
Okay.
it turns out to be an interesting question for a couple reasons. So if you were to take this program and probably compile it on your computer and run it, you probably would get 15. And so you probably think, hooray, I got the answer right. And in fact, if I did that on my laptop, that's what I would get also, 15. The problem is if now you take this same program, no changes to it, compile it on a 64-bit machine, you wouldn't get 15. In fact, what you would probably get is an access violation or something like that.
Now, why on earth is that the case?
Yeah, it turns out that there's some weird things that sometimes go wrong, and this is a problem that I like to show people to illustrate kind of some of the potential problems when you go to 64-bit. And this turns out to be one of the more subtle problems. Most of them are a lot more in your face than this. So let's go ahead and take a look at this code again, and I can kind of show you why the answer to this question is really depends on what kind of computer you run this program on. And there's a couple of things, if you look at this program, there's a couple of hints that kind of will give away why this problem is so difficult. And one of them is right here. Why did I use unsigned int there? I used int up here for minus 30. Mm-hmm. Then that time I said, let's do unsigned int. That's a pretty big hint right there.
Yes.
Actually, that turned out to be the real issue. So now let's go ahead and look at this expression. This is where all the excitement is. So we go ahead and we do x plus y. So we're going to go ahead and add x plus y, and that gives us minus 10.
Mm-hmm.
The interesting question is, what is the type of that expression?
So you're adding an int plus an unsigned int.
Right. It turns out that in both C and C++, the result of this expression is going to also be an unsigned int. So the end result of this is an unsigned int, but it's an unsigned int with the representation of minus 10. Now, to be perfectly honest with you, I don't know what the bit representation of minus 10 is, but you can imagine it looks, something, like 1, 1, 1, blah, blah, blah. In any case, what it is, it's 32 bits with a 1 in the high order bit. As an unsigned number, it's a very big value.
Mm-hmm.
As a signed number, it's minus 10. So now, why does this work on 32-bit? Because on 32-bit, you end up taking this 32-bit value P2 and adding it to a 32-bit representation of this bit stream, which it really doesn't matter if you interpret it as -10 or whatever big number it is as an unsigned value. The end result is going to be the same 32 value, which is going to be 10 less than what it currently points to. But on 64-bit, what we're going to actually do, because this value is unsigned, we're going to 0 extend this value out. So what you end up doing is you end up taking P2 and adding some ridiculously large value. It's probably something like, 4 billion something. And then you're going to dereference that value here, which is going to be pointing into the middle of some, bad space. And at that point, you'll probably end up with the access violation. Now, had we made this an int value here instead, what would have happened here is instead of 0 extending this, we would have sign extended this value. Because it's a signed value, you go ahead and you sign extend it. Now when you do the addition with P2, it'll effectively be a subtraction of 10, and the results would have been 15 like you expected. So watch out for this int, this unsigned versus signed arithmetic. Sometimes, and then of course the arithmetic with the pointer, because sometimes this can get you.
Now, theoretically, static analysis tools could be used to find these types of problems.
Absolutely.
At compile time.
Yep.
And so,
yeah.
Are we going to do? So, are we doing that?
So right now at the moment, we do have, for example, a switch which is /WP64, which currently does not detect this because this is especially onerous in 64-bit. We currently don't detect this with WP64, which is why I do like to make a point of going out and letting people know that this is something that they need to be aware of. If they are using both unsigned and signed ints and using the results of those computations to then do arithmetic with pointers. So,
and I can't, in this particular case, there's really no reason to qualify it as unsigned, is there?
In this case,
it's just an example.
Right.
But in a real world scenario,
we've had customers actually scratch their heads because of this and just have no idea what was going wrong.
Yeah.
And eventually, they looked at the problem and saw, okay, we have this.
It took me long enough to see that the answer was 15.
Yeah, and they can be very, you can imagine in a real code, if you're not, if you don't know, first of all, this rule that x plus y, the result of the signed unsigned addition is going to result in an unsigned value. For a lot of people, there's just no reason to have that knowledge in their head.
Yeah.
It's not something that typically presents a problem. And then having to know the distinction between, if you sign extend values going to 64-bit or you 0 extend them. There's lots of little bits of information that people may not necessarily have in their heads, and when it hits in subtle ways, the end result of the problem here, could end up being an access violation 20 lines down the road. And you have to start piecing together.
And you have to debug it and try to figure out what caused it.
Absolutely.
And that's a headache.
That is a headache.
And not to mention, an access violation kills your app.
Yeah, kills the application. Yeah.
You don't handle access violations typically.
Yeah, typically, yeah.
That's not a good idea.
Yeah, there's usually not much to be done anyways.
Grant, how are you doing? We're just going over some 64-bit code. We're here again. This time this is 64-bit.
Oh, that's cool.
So we're just talking about what's wrong with this code.
What's wrong with the code? Unsigned int. Yep. Yeah. See? That'll get you. You got all these other bits out there.
Yeah.
You don't even know it.
Yeah, there's bad stuff out there.
Yeah.
Sometimes like the deep blue sea.
Definitely.
It looks nice and calm, but every once in a while there's a shark.
There certainly is. Are there any other examples?
This is probably the
classic.
I think this is the hardest example for most people who don't know what the problem is to necessarily grok, because most of the other problems, probably the most classic problem is the truncation problem, which is that you end up taking a 64-bit pointer value and assigning it to a long or an int, and those are 32 bits, and so you end up losing the upper 32 bits. And all of a sudden now you're walking around thinking you have the full 64 bits, and you maybe pass it back to a pointer, and then you're pointing off into memory that that you don't own, or that you don't have the correct data in. That's probably
the
the
beauties of the CLR.
Oh yeah.
Beauty of the CLR.
That's probably the most canonical problem.
Sure.
Now, what about structure alignment issues? Do you get the same problems with that, or is structure alignment the same?
So structural
32-bit to
alignment
64?
is different. The good thing is if you don't do anything funny with your structures, the compiler takes care of it.
Right.
So we'll go ahead and align everything on the right boundaries. But if you use something like pound pragma pack and say, I want to pack the structures, at a 4-byte boundary or something, pointers need to be 8-byte aligned. So now all of a sudden you could end up with alignment problems there.
What about union structures, where you have several different types union together?
You can also have problems with union structures, although typically the problem with union structures won't be the alignment problem. The problem we see with the union structure is, in fact, if I can write on the whiteboard again.
Oh, I can almost see what's going to happen.
Yeah, you end up doing something like, often you end up doing something like this, where you have a union, and you might say long value, and let's make it, I will leave it value. My names aren't the greatest in the world. And then you might also have something like int pointer, and you might call this like mask. Probably be the opposite way. And so in the past, what you thought that these two values were total aliases of each other, right? They're both 32 bits. If you go ahead and zero out value, you zero out mask. Although now in reality, this is 64 bits, so it's really stretching out to there, whereas this is just 32 bits. So now all of a sudden, if you go and try to set some pointer value by accessing value, you're only getting half the bits. The other half of the bits are just hanging free, and you aren't actually modifying it.
In a 64-bit word, is it still LSB? Well, now LSW, least significant word. And then what's significant word in an Intel architecture?
It's the same. Yeah.
Okay.
The Indianness of it has
The
remained the same.
Indians. Okay. Okay, so you'd still be hitting the lower value. When you have shorter value, you're still hitting the low value.
Right.
Okay. Well, that's really good if you want to know the right order to hack.
Right.
Pointers. You want to know where the high is and where the low is.
Yeah.
In the low word.
No.
Well, no, that's what you want to do. Why use C++? Unmanaged C++ if you're not going to do this. You can use managed C++. If you want to mess with your pointers. If you're never going to mess with your pointers, use managed.
You got it.
I think.
That's exactly correct. And of course, in the managed world, this type of example has no meaning.
In the managed world, actually, this type
Can you
of
get in trouble?
well, it depends. So in verifiable code, you can't do that pointer arithmetic.
Exactly.
So you won't get in trouble there. Although you can write non-verifiable code and still do pointer arithmetic. In that case, you will still hit this exact same problem.
In an unsafe block.
In an unsafe block, right.
Sure.
But if you're writing safe code, verifiable, you should be safe from this.
And you wouldn't get this.
Oh yeah, of course you would.
Yeah.
and even more important, you wouldn't be writing that.
No.
Right?
No.
No. Exactly.
So,
In fact, it's-
although maybe it'd be disposed.
yeah, that's not the same.
Yeah.
No, it's not the same. No.
We won't get into that debate. But that's actually a
Deterministic
good debate.
versus non-deterministic.
Yeah, I mean,
The structures.
you got it. And that's actually, I know something that the C++ team has been working closely with the CLR team
Yep.
to try to come up with a reasonable approach so that you can fit into that world
Absolutely.
in a more comfortable way.
Yeah.
And so they are working on it and thinking about it.
Yeah, well, we will have deterministic finalization, stack-based semantics. So that's, a lot of people have been asking for that, and for a long time, people didn't think it could really be done. So I think people will be...
Yes. How is it?
You
How
know,
did they pull it off? Do you know?
to be honest, I don't know
Is that someone
enough of the
else to get in
details
front of the camera?
to say in front of an audience of exactly
Sure,
how
that's
it's
fine.
done. So
That's fine.
I wouldn't try to...
Yeah.
That's fine. It's probably quite abstruse what they had to do.
Obtuse?
Abstruse.
Oh.
It means it's the same
Abstract
thing
and
as
obtuse?
Yeah, it's more than obtuse.
Okay.
It's abstractly
word.
obtuse.
Yeah.
It's a real word. But I use it a lot because a lot of the stuff that happens way down in the system is abstruse to me. But that's really cool. This is a good one. And remember that out there, people. Unsigned integers, not a good idea in arithmetic pointers on a 64-bit.
Or actually, we should say it's not unsigned or bad.
Yeah.
But when you have unsigned and signed arithmetic, know the semantics of it. Because, when you start playing with them, if you don't know what the semantics are, they can do some things that are different than on 32-bit. But for example, if you didn't have a negative value here, and this was unsigned, that would be all goodness as well.
True. Absolutely.
There's nothing wrong with unsigned values in and of themselves.
Just mixing with
Yeah. What is the behavior in 64-bit? Does it change when you assign a unsigned or a signed object to an unsigned it?
So
Does the semantics change at all?
the semantics don't change, but the behavior does change because of the way 64-bit represents pointers.
Right.
And so, and this is exactly this problem here, that what ends up happening is you end up adding a signed and unsigned value.
Okay.
The end result, the type of this expression is unsigned. And because the end result is unsigned, and the end result is what would be a negative value if it were signed, when you add this to now a pointer, which is 64-bit, you don't get the sign extension. And so you end up now adding to the pointer this really
See,
large value.
I would have learned this if I walked in about
Yep.
10, 15 minutes ago. Okay.
Yeah.
That's an interesting behavior. I can see how it can really get you. Be a bummer to track down a huge program too.
Oh yeah. And what we typically also tend to see happen is when people hit this, they don't hit it once, right? It's throughout their code, right? It ends up being an idiom that they used in their program.
Now, that's actually a beautiful segue to the next question. And that is, what are some of the gotchas, other gotchas you've seen customers
Right.
going?
Yeah, so some of the other gotchas that we've seen, we end up seeing a lot of kind of just things that are, in many ways, I think, one-offs. And that I can't imagine other people doing stuff like this, but you really never know. Because, people do crazy things with their code. One of the things that, that we've seen, for example, hash functions, that when you go to a 64-bit address space, all of a sudden don't end up hashing very well. Because they were relying on, a 32-bit hash function, so they end up having these collisions when they move to 64 bits and they're taking the size of a pointer as part of their hash function. Again, that's something that I don't expect to see a lot of people do, but people can hit it. You often see code that does things like, if j is not equal to, and they'll do something like this. And they'll put 8 of these, right?
Thinking.
And they think that's -1.
Yeah, that would be -1 usually.
Right. On a 32-bit machine,
It would be.
that's -1. On a 64-bit machine, it's just a really big number,
Yeah.
right? Because, you need to write, on a 64-bit machine, you have to write 16 of those for it to be -1. So, you see people with code like that. Why would they do that?
The only way I say why they could do that is if actually that was a variable and it was getting that and they had no control over it, right?
Well, maybe they didn't
Runtime,
know
they'd be screwed.
that was their test code, or I don't know.
People do weird things like, I mean,
Okay.
if you look, maybe one that actually is a bit more common than that even now is people that will do things like if j, well, probably should be lowercase, if j, and they'll do something like and what they want to do is pull off the most significant bit. And then what they'll do in this case is they'll do, 8, and then they'll do 7 zeros.
Because they just want to know if the value's negative.
Right. And again,
Again, they're thinking they're being really clever with their bit manipulations
Yep.
for speed, rather than saying if j less than 0.
right.
Yeah. And
So
so,
for speed.
they're helping. Yeah, they're trying to optimize the code. And I bet you there is code, right? Where when they did that, in the version of the compiler they were doing on, that was like way faster. That of course was probably a 386 processor, and some version like 5 of Visual Studio, C++. Maybe that was faster,
Yeah.
and it really mattered. You got that one extra little and or load out of the processor. It made your code that much faster, but now it's a legacy
Yeah.
of old code that people probably didn't even know what was going on.
Yeah, a lot of times people just write less than great code.
Yeah.
You know.
Or they're writing in an environment where it really is bit specific. So we're talking kernel mode.
Right.
I mean, in that case, those people, all of their stuff, or not all, but they have to spend a lot of time.
Right.
For example, 64-bit drivers.
Yep.
You have any of those guests here today?
You know, I don't know if there are some 64-bit driver writers out there.
Okay.
There may be. So,
That's interesting.
yeah, one of the places. Actually, no.
Okay, fine.
Yeah.
That's cool. That's called an aborted thought.
Yeah.
We just witnessed an aborted thought.
Yeah, we don't want to get into that.
I like that.
That's good.
So what else? So that does look like crazy code. Like you're saying, maybe for performance reasons, that's fine. What else? Anything else? Any like major design mistakes you can make? Not just code?
You know, probably the single biggest design mistake is the one that me and Volker had alluded to before, which was people not taking into account their library dependencies. So they go and they start planning to do this huge 64-bit migration, and everything looks great, and they're doing all the right stuff, except for the fact that they didn't realize that the core DLL they need isn't on 64-bit. That's probably the biggest design problem that we tend to see, is that people just totally miss the that whole boat. They didn't really plan well. In terms of actual architectural, developing the product and laying things out, I don't think I've seen any specific design problems people have had, in the sense that typically if you have a good 32-bit design and architecture, it transfers over to your 64-bit platform as well. So,
Now, which brings up another question. How many pure 64-bit applications are there out there? So from the ground up. We've been talking about migration all day.
right. So these are applications that are written 64-bit, and there's probably no corresponding 32-bit application that exists. That's a good question. Considering that we only have the Itanium version of Windows available, and the x64 hasn't come out yet, I don't think that there's a whole lot. Off the top of my head, I couldn't give you a number.
That's fair. It's kind of a random question. But it'd be interesting to see kind of what people are thinking.
Right. I think right now most of the effort is concentrated in moving 32-bit applications over, because obviously if you're in a commercial business, most of your sales are still going to be on 32-bit. You're comparing 100 million or however million 32-bit versus how many exist on 64-bit. Eventually, though, as the market begins to shift, you'll begin to see the 64-bit applications take precedence, and eventually there will be that point where there are 64-bit versions, but no 32-bit. Actually, I did think of one that actually Microsoft is doing, which is there's a compute cluster edition of Windows that we're developing. And this compute cluster edition of Windows, version 1 is only going to be available on x64.
Can you explain a little bit what that is? I've not heard that before.
Yeah, so this is actually coming out of the newly formed High Performance Computing Group from Microsoft.
Okay.
And so the idea is that one of the big things that's catching on nowadays in the industry is compute clusters. And so what the idea here is that you effectively get commodity computers, often a rack mount configuration. And these are going to be x64 based, and you basically tie them together with some type of interconnect, whether it's a standard Ethernet or InfiniBand, and then now you can basically treat these as your own personal supercomputer. And the cool thing is, you can now go ahead and put together a machine with, 32 processors, at a very cheap price, and you can get the same power that people are getting at the, supercomputing centers. And, this is stuff you're building out yourself. Historically, this has been kind of the Unix world. People have done that with Unix-based operating systems. And we saw that one of the big things that was missing is that the support for managing these systems wasn't great, and the tool support for these systems wasn't great. And obviously, Windows kind of, when you think about having an easy to manage, configure, work out of the box system, you think Windows. And so we said, let's leverage all of the technology that we have at Microsoft and put together a SKU that's focused on building out these compute clusters. And so that's what the High Performance Computing Group is doing.